In this video, we'll discuss the process of figuring out where the differences lie after we found a statistically significant ANOVA result. So the predicate for this particular section of our lecture is that we just found a significant ANOVA. And that's when this section begins. So we don't really use these procedures if we haven't found a statistically significant ANOVA. But if we have, then these procedures come into play. Now, there are a whole ton of different procedures that we can use. And in fact, what I consider to be the best one is called Tukey's procedure. But in this case, we're going to discuss the simplest one possible, which is Fisher's LSD. And yes, that is the actual name of it. It stands for least significant difference. And we're going to talk about where that name comes from. So the idea, remember with ANOVA, we compared all the means in a single test. Well, now we want to figure out which of the groups are different. So what we're going to do is we're going to pair up every pair of the means. So we're going to think about if we have three groups, 1, 2, and 3, we're going to find all the pairwise combinations. So sometimes you'll hear this called pairwise testing. By pairwise, what I mean is I and J could be group 1 and 2, or groups 2 compared to 3, or group 1 compared to group 3. The order doesn't matter, so like 2 compared to 1 is the same as 1 compared to 2, but we want to make sure that these are distinct groups, so I also wouldn't compare group 1 to group 1. Typically, as we just mentioned, for 3 factors, we'll have 3 tests, group 1 and 2 compared, group 1 and 3 compared, and then group 2 and 3 compared. To calculate our test statistic, we're going to use the same MSE from our ANOVA, and we're going to use the same numerator that we would normally have. The point estimate for our group differences is still x sub I bar minus x sub j bar. So this should look very familiar. This is from our 2-sample test. And in fact, what Fisher's LSD is running is literally a whole bunch of 2-sample t-tests. So all we're doing in this section is 2-sample t-tests comparing each of the 2 groups with all of the different pairs that we can make from our K groups in ANOVA. And then our standard error is changing. We're just having this MSE term in our standard error where previously we didn't have that. So for the p-value approach, we still reject if p is less than 0.05. And because this is a two-tailed test in our 2-sample t-test, we do the same exact cutoff criterion, which is if it's less than the negative cutoff or if it's greater than the positive cutoff, we reject the null. So again, think about our curve. We've got a top and a bottom cut, and if it's bigger than the top cut, if it's smaller than the bottom cut, we reject. Interesting to note here, and this is important, that the degrees of freedom for the t-distribution is this capital N minus k, or n sub t minus k. So notice that this is the degrees of freedom from the error term is what we're using for our t-distribution. Now what's kind of interesting here is how this tends to be constructed. So if you just did the regular t-tests, that would work great. But the term LSD comes from the least significant difference. So I'm going to move to the chalkboard to draw this out and demonstrate where this term really comes from. So I'm going to start by writing out my test statistic t, which was x bar sub I minus x bar sub j over the square root of the MSE times 1 over n sub I plus 1 over n sub j. So this was my test statistic t, and then I would compare this to t of alpha over 2. And again, I'm comparing if it's bigger than the bigger than the large cutoff or smaller than the small cutoff. That's when I would reject on either side of here, and then the middle is fail. to reject, is how I'm constructing this. Now, another way to think about this is to compare the absolute value of this test statistic and see if it's greater than the absolute value of my t statistic. And this is the exact same thing. These are equivalent to one another. So this is a nice way to phrase this and actually forms the foundation for how we're going to create our test statistic, or excuse me, this Fisher's LSD. So what I'm going to do is just write my full term here, the absolute value of x sub I bar minus x sub j bar. This is the only part that can be negative because a square root can't be negative. MSE times 1 over n sub I plus 1 over n sub j. And this is going to be greater than my cutoff t sub alpha over 2. And so what we're going to do, and this is kind of ingenious, is that instead of doing this calculation every time, because the only thing that's going to change on this calculation is this top part. This top part's going to change with every sample, but this bottom part is all going to stay the same because the MSE is not going to change. Now the n sub I and the n sub j might change, but if it's a balanced design, even that's not going to change. Nothing in red is going to change. So what we do is we focus just on the part that's going to change to make our calculations a little bit simpler. I just look at the mean difference, and I want to see, is the mean difference big enough to be significant? Now, how I get the mean difference alone on its own side is multiplying both sides by the stuff in red. So I take my t sub alpha over 2, and I multiply by that stuff in red, the square root of the MSE, times 1 over n sub I plus 1 over n sub j. And this becomes how I compare my mean difference over here on the left to a cutoff. So if my mean difference is bigger than the stuff on the right-hand side, then this is considered to be a statistically significant difference. So the stuff on the right-hand side is the smallest difference possible that's statistically significant, or we can call it the least significant difference, this LSD. So when we calculate LSD, that is where it's coming from in this particular case. And LSD is just this t times the MSE of 1 over n sub I plus 1 over n sub j. So we calculate this least difference, and then we can compare all of our pairs of means to the smallest difference that's significant. And if the difference between the pair of means is bigger than the smallest significant difference or the least significant difference, then the difference between the means is statistically significant. So pretty much we look at all the differences between all the pairs of means and compare it to this value and see, is it smaller, in which case it's not significant, or is it bigger? Is the difference large enough to be considered significantly different? Pretty darn cool. And not just pretty cool, but saves us a lot of work. So we compare to this LSD value, where we calculate that again by multiplying both sides by the denominator in our test statistic. So let's go back to our old example. And actually, if you want to pause and give this a shot, please feel free to do so. Pause, calculate the LSD, calculate all your pairwise differences between the means of the groups, and see if you can figure out which ones are statistically significantly different. All right, coming back to this. So first I calculate my LSD. I'm going to use alpha equals 0.05. Capital N minus K, so my total sample size 15 employees, managers minus 3 is the number of groups, the number of locations I was looking at. So that gives me 12 degrees of freedom. And then I calculate T sub alpha over 2. That gives me 2.179. Now for the LSD, I plug in my MSE that I calculated previously from this problem. I have my 1 over n's that I include, And then I calculate my least significant difference to be this 6.98. So 6.98 is going to be the smallest significant difference that I have. So any difference that is bigger than 6.98 is statistically significant, and any difference that is smaller than 6.98 is not significant. Write that down. If this is confusing, write that down. Any difference that's bigger, any pairwise difference between the means of the different factor levels or of the different groups that is bigger than 6.98, this LSD is statistically significantly different. Any difference that is smaller than this is not significantly different. So let's check. Looking at the first two groups, again, is it bigger than 6.98, the absolute value bigger? Well, looking at this difference, the size of the difference is 13. The absolute value of this is 13. So yes, the size of this difference is bigger than 6.98. Now it's in the opposite direction. That is, x2 is bigger than x1, but that's okay. We're just looking at the size of the difference. So in this case, the size of the difference is bigger than 6.98, and that means we have statistically significant difference between plant 1 and plant 2. Or said another way, there is enough evidence to conclude that the mean number of hours in plant 1 is not equal to the mean number in plant 2. Which one's bigger? Well, I can just look real quick. The mean in plant 2 is 55 hours a week. The mean in plant 2 is 68 hours a week. Oh my gosh. So the hours worked in plant 2 is statistically significantly larger than the hours worked in plant 1. All right, well, now let's compare plant 1 to plant 3. So looking at this, again, if it's the difference, the absolute value of the difference is bigger than 6.98, it's statistically significant. The absolute value of the difference is 2, so the size of the difference is 2, and there is not a statistically significant difference between these. That is, there's not enough evidence to conclude that the mean number of hours worked per week in plant 1 is different than plant 3. Now, in our sample, plant 3 worked an average of a couple more hours. But again, we're trying to make conclusions with statistics, not about the sample, but about the population, about data that we don't even have, about everybody. And in this case, we just don't have enough evidence to make that conclusion. All right, for the last comparison, we're comparing plant 2 to plant 3. So looking at plant 2 and plant 3, I see that the absolute value of the difference is 11. So plant 2 works 11 more hours than plant 3. The size for a significant difference is 6.98, and 11 hours is well above 6.98 hours. So this counts as a statistically significant difference. That is, there is enough evidence to conclude that plant 2 and plant 3 have a different number of hours that the managers work per week. Which one's higher? Well, it looks like plant 2 has a statistically significantly higher workload than plant 3. And taking all this together kind of in conjunction, it's important to consider what does this mean? Well, looking at this, plant 1 and 3 were pretty close together, 55 and 57, and they weren't statistically significantly different. But plant 2 was way higher than both of them. So plant 2 is kind of off in its own little world, and something's going on at plant 2 that makes the hours worked per week by the managers higher overall. And again, we're making these conclusions not just about the sample that we took of the 5 managers, but about the population of all of the hours worked by all of the managers, assuming that our sample was randomly selected. Now, we want to be a little careful here because, again, we don't have anything causal. We're not saying that plant 2 causes this. We're saying that for whatever reason at plant 2, this is going on. So it could be causal, it could not be. But we do know that the effect is happening, and that's kind of the weird thing. You don't need causal claims to be able to observe an effect. You just don't know why the effect is happening without causal claims. So this has been a discussion of how do we break down group differences in an ANOVA after we found out that there was a statistically significant difference. Again, ANOVA tells us there is some difference somewhere. It doesn't tell us what the difference is. Using this post hoc procedure, the Fisher's LSD test, which stands for least significant difference, we're able to calculate the size of what is the smallest pairwise difference between means that is statistically significant, and then look through all of the different pairwise differences and figure out where are the differences happening. In this case, the difference was happening with group 2. Group 2 was a lot higher than the other two groups. Now, it's important as we talk about conducting a lot of these different tests that we address the fact that as we run each test, we increase the amount of type 1 error. Well, what does that mean? That means that if I compare more groups or do more of these comparisons, that the probability of a type 1 error increases. And actually, this is why we only run this test after we have found a statistically significant ANOVA, which accounts for this. So you can calculate what the type 1 error is on k-1 pairwise comparisons using this particular formula. You find your alpha rate for each of the individual tests, and then you can plug it into this formula, and it'll tell you what the experiment-wise type 1 error rate is. That is, what's the probability that anything made a type 1 error in your whole experiment? And this is really interesting and useful to know. There's several other corrections that you can make. Fisher's least significant difference doesn't account for this at all. My favorite procedure, Tukey's, does account for this very well, and there's other corrections like a Bonferroni correction that you may hear of that do a very good job of addressing the type 1 error rate. Bonferroni is really nice because you can use it whenever. Pretty much you just divide your alpha by how many tests you're doing and use that as your new alpha level. Actually, that's all of Bonferroni. Divide alpha by how many tests you're doing, and that makes sure that this experiment-wise error rate stays below whatever alpha you want. But it's a little bit like using a chainsaw for fine woodworking. It doesn't always create the most polished results, but it does work. So it's kind of nice. In any case, this is not particularly meaningful when you're running your pairwise comparisons as a post hoc procedure. That means after the fact, after you have found a statistically significant ANOVA. But it is of concern if you are just running a whole bunch of different tests looking for differences. This is also more a concern when k gets large. So for k equal to 3 or k equal to 4, this isn't a particularly big concern. But let's say we were testing every location in the country. So I was looking at hundreds of locations and hundreds of pairwise comparisons. In that particular case, I'd want to take much, much more care about controlling this family-wise type 1 error rate, because that is going to get quite large if I'm looking at, if I have hundreds of businesses, we might be talking about millions of comparisons. That could be something that I is going to drastically increase my type 1 error rate and has to be accounted for. All right, well, this has been the video discussing how we break all this down after an ANOVA, how we figure out where the group differences are, and a brief discussion of our type 1 error rate and the risks involved with that. Again, pretty minimal when we've got just a few comparisons if we're doing this after an ANOVA. If you wanted to do a hack dash way to control this, you could divide alpha by the number of tests you're running. That correction is called a Bonferroni correction. You then use that new alpha level and compare all your p-values to that. Next, we'll begin talking about how do we incorporate multiple variables into the ANOVA, or we'll jump straight into R depending on how much time we have. But if we're able to, the way in which we incorporate multiple variables into ANOVA can be very useful and save us a lot of time and money.